So X-rays. Everyone has had experience with or knows about X-rays, but do we really know what happens when doctors put us under these machines? So in the basic X-ray tube, there's a cathode and anode end. Cathode end is where the negatively charged electrons are, and the anode end is where the tungsten or copper plate is. Electrons accelerated from a heated cathode toward a metal anode by a large potential difference. So changing the filament temperature changes the electron current. A hotter cathode releases more electrons than a cold one. This determines the intensity or brightness of the other X-ray beam. Since one electron will produce one X-ray photon when it strikes the anode, more electrons flying through the tube means more X-ray photons emitted from the tube. So the voltage across the tube determines the kinetic energy of the electrons when they strike the anode, which in turn determines the penetrating power of the X-ray photons. More energy per electron means more energy per X-ray photon, and thus greater ability to plow through matter, which is the skin and fluids of your whole human body. So there's actually two types of X-ray generation, and one of them is Brim-Strahlung or breaking. And this is when an electron passes near the nucleus of the tungsten or copper plate and is slowed, in which its path is deflected. Energy loss is emitted as a Brim-Strahlung X-ray photon, and this is what penetrates the body to give the picture of the bones. Approximately 80% of the population of X-rays within the X-ray beam consists of X-rays generated in this way. You can see in the picture how the electron coming from the left side, from the cathode end, hits the nucleus, and parts of it is actually continuing on the circuit, while other parts of it turns into X-rays generated into photons. The second type of X-ray generation, known as characteristic X-ray generation, this happens when a higher energy electron collides with an inner shell electron, and both are ejected from the tungsten atom, leaving a hole in the inner layer. This is filled by an outer shell electron with a loss of energy emitted as an X-ray photon. You can see here how Brim-Strahlung and characteristic radiation differ and how intense their X-ray beams are, depending on the density of the body part they're trying to penetrate. Brim-Strahlung are more often used on less dense body parts such as arms and legs, while characteristic is mainly used on chest and stomach areas. So recall how wavelength is the distance between two crests of each wave, and frequency is the number of crests that pass by you in a second. The longer the wavelength, the lower the frequency, and the lower the energy of the photon. So as you can see here, X-rays have a much higher frequency or shorter wavelength than radio waves, microwaves, which allows them to pass through and penetrate the body, skin, and matter. Here's a very basic representation of the X-ray tube and its circuit. And if you can recall, electrons are accelerated from the negative end of the power supply, traveling through the shield or the window of the X-ray tube into the cathode end and into the anode, or towards the anode, as negatives are attracted to positive, positive attracted to negative, and which are then shot into the body. So the photons themselves that are deflected off of the tungsten or copper plates and the anode side of the X-ray tubes, they have momentum. And a man named Thomas Planck actually discovered that photons have energy. The equation energy equals Planck's constant times the frequency of the wavelengths of the waves, X-rays. And then Albert Einstein discovered that energy and momentum are related. The equation energy squared is equal to momentum squared times the speed of light squared plus mass squared times the speed of light cubed. And then since photons are massless, this equation reduces to E equals PC. And if you combine Planck and Einstein's equations, it comes out to PC is equal to HF. And that is momentum times the speed of light is equal to Planck's constant times the frequency of the waves. And then if you solve for momentum, P equals HF divided by C. And you can recall that one wavelength for an X-ray is equal to speed of light divided by the frequency. You plug that into the equation, and you get momentum is equal to Planck's constant divided by lambda. Lastly, I just want to touch up on the conservation of energy in the X-ray production, and how at the cathode end the electrons start with potential energy and slowly or rapidly accelerate, gaining or transferring that energy into kinetic energy at the anode end, losing some of that to thermal or heat energy while the photons are emitted into the body.